let me say a few words about Matthew. He has a really interesting background. He has a PhD from UC Berkeley in neurosciences, but he also has degrees in computer and electrical engineering, also a degree in biology, and a degree in Chinese language and literature. So he is very multifaceted. And the program that he has developed, he's going to talk to us today about the brain structure and the underlying theory, the theory that underlies his development of curriculum. But let me just say a word or two about that curriculum that he's developed for students. It's the ST Math program, Spatial Temporal. So rather than using words to learn math, you use computer games and spatial temporal reasoning, looking at space and time. So it's a completely unique new way of doing things. And it's a way that has been really verified. Its effectiveness has recently been verified by a study of 150,000 students. Independent researchers looked at this and found that it was about a half a standard deviation better. These students performed about a half standard deviation better on state standardized exams. So not surprisingly, with that kind of success, it is something that is widely used. Matthew's own children are in a school that uses it. My colleague Jeff Phillips' students are in a school that uses it. It's used across the country by over 1 million students in over 4,000 schools. So it's very broadly used. So without further ado, let me have Matthew start his talk, and he's going to talk about the underlying neural structure and how this underlies this development. Yes?
I'm sorry, I didn't hear your name.
Oh, I'm sorry. Vince Coletta. I'm director of the Center for Teaching Excellence.
I thought I was going to give a talk about Chinese language and literature.
Oh, that was the one tomorrow
That was the
night.
next talk. Okay.
Yeah.
All right. This first talk about neuroscience behind ST Math. Okay. Great. Well, this is the 20th anniversary of the Mind Research Institute, but I've been working on this for 25 years now, and I thought I would be a lot further along than we are today. One of the interesting things is that there's this exponential growth in technology, and everyone knows this, Moore's Law. Things grow exponentially with technology, okay. And instructional games to teach math is also going through the roof. And look at student test scores over that same period of time. And when I started, I didn't start way back here, but when I first started looking at this, it was obvious that computer games would be a great way to teach mathematics. It was just like, duh. But a lot of people were skeptical. But you talk to any computer scientist, and it's, of course, if you make a game to teach math, they're going to learn math. Yet, almost no games that have been built to teach math can show any verifiable large-scale results. Why? Why is that? And so I want to talk to you a little bit about that. So over the 25 years, I've, with my team, have built multiple thousands of games. And the vast majority of them have been miserable failures. Some of them even resulted in a decreased understanding of mathematics after playing the game. It is really, really hard to make a game that teaches you mathematics better than what you would be able to learn otherwise without that game. And so what I want to share with you is a framework that we figured out at Mind Research Institute that underlies what is now a wide-scale, highly effective approach, and is also giving us insights into taking things to the next several levels, which is really exciting. We're right now working on teenagers and what makes for a highly effective learning environment for teenagers, and it's very, very exciting. So I want to start off with the brain. I've removed the neocortex from the allocortex. You don't normally want to do that for students, but just to make it clear, We consider 4 major neural subsystems, and that really helps thinking about how to create a highly effective environment for learning. And so I want to highlight these neural subsystems. I also want to caveat for any neuroscientists out there, these are not super exact, nor are they, I think there's so many fallacies of pointing to a part of the brain and says, this part of the brain does that. That usually leads to bad misconceptions about what's actually happening in the brain. It's done a lot. So I'm going to make that mistake, but I think it helps in understanding, or at least guiding you on making good decisions on creating interactive learning environments. So here are 4 different neural subsystems. This big area, most of your neocortex, is devoted to creating what we call perception action schemas. And so the brain is divided into 2 parts. So you have the anterior and posterior cortices, and this right here is the central sulcus, the Rolandic fissure. So that's the front part of your brain and the back part of your brain. Which part? One of those parts deals with perception, and the other part deals with action. So how many in this room thinks that the front part of your brain deals with perception predominantly? Huh?
It doesn't.
Doesn't. How many thinks the back part of your brain deals with perception predominantly? Yes, it does. Okay. And so, so this is all perception back here. This is your primary visual cortex, your auditory cortex. This is your somatosensory cortex. It's all processing sensory input. And then if you pass this Rolandic fissure, you're now in your motor cortex, controlling your muscles, and your prefrontal cortex where you're planning out action. And there are these reciprocal connections that go back and forth, and create what is called a perception action cycle. And that term is coined by Dr. Joaquin Fuster at UCLA. And it underlies the development of these connections between perception and action, which form the basis of learning and cognition. And so things that you understand about these chairs, and you know that these things move down, and you kind of know how to sit on one of these chairs. You have a whole bunch of motor actions and perceptual actions to know what type of chair this is, and that forms a perceptual action schema that allows you to interact with such a thing. And so you have to build these perception action schemas for all kinds of things in the world, and in mathematics, that is also the case. You do also have these perception action schemas. Often we dissociate action from perception in math class, which is a mistake. But so anyway, so what I'm showing here, this green area, is devoted to perception action schemas. This next subsystem here is your prefrontal cortex, and that's works a little bit different from just building up these schemas. So here, to build up a schema, you do things over and over and over again until you've kind of built up some circuitry that knows how to perceive things and interact with those things. And it takes many, many repetitions to build up a schema. Here, your prefrontal cortex, you're not interacting necessarily with routine problems. Here you're interacting with non-routine problems you've never seen before. So, creativity, planning out multiple steps, combining multiple schemas together to plan out a solution. So it's a different type of system that you need to develop. All right. Down here, this is part of your medial temporal lobe, and I've kind of highlighted 2 major regions, your hippocampus and your amygdala. But this is episodic learning. You can kind of think of this hippocampus almost like a camcorder that's kind of recording episodes of your experience. And then you often, during sleep, you consolidate those episodes, if you've seen them over and over again, into schemas in your neocortex. But these episodic learning is also very different because you can instantly learn with your hippocampus. It's super fast. But your hippocampus likes to absorb these things that are emotionally laden. That's why I've highlighted this amygdala. And things that are interconnected with space and things that kind of form a story about your life. And so the type of learning that happens here is you should think of it differently as trying to develop your prefrontal cortex or these higher association areas of your neocortex. And then this final subsystem I've labeled here academic discourse. This is your language subsystem, and I've only highlighted your Broca's area and your Wernicke's area. The language subsystem is much more complicated than just those two areas. It's interconnected with everything. But your language subsystem you can think of as a fourth neural subsystem. And one way to make sense of it is, does it resonate with you if I say, you never really understand something until you've put it into your own words? Until you've be able to describe it to somebody. Okay, so if you believe that, then you are a believer of this fourth neural subsystem. And so each of these subsystems, you can look through history at where the techniques for teaching have dominated one of these subsystems. So this is kind of like very traditional teaching, rote memorization, do things over and over again, do these math problems over and over again until you've built up an action schema and a perceptual schema for how to do long division or whatever it is that you're doing. So then you're a believer in this perception actions subsystem. And there's other people who say, no, I don't want you to memorize things. I want you to be creative and solve problems you've never seen before. So you're a prefrontal cortex type of person if you think that way. Then you have people that are sometimes sciences, or if you're studying Chinese language and literature like I did, big believers in experiential learning. So I want you to go on a field trip and experience it yourself. I want you to do this experiment so you can experience what happens. I want you to go to a Chinese New Year celebration because you don't really understand what Gong Xi Fa Cai means unless you've gone to a Chinese New Year celebration. And so for those people, they really believe in this hippocampal subsystem. And then there are people that want you to talk about it. I want you to explain your thinking. Math talks, CGI. These are math programs that are a lot about talking and explaining your thinking. But really what you need to do is you need to do all of these things. And they should be an integrated system that incorporates all four of these neural subsystems. And it's a very useful way of designing highly effective learning environments. So let's walk through some of these things. So let's start with perception action cycle. How do you avoid all of the problems of traditional drill and kill approaches to teaching math, which directly hits this perception action cycle? And the one thing that you should do is eliminate multiple choice. And let me give you an example for why I believe so strongly in eliminating multiple choice from the learning. Multiple choice might be okay in assessment, but from a learning perspective, it's very problematic. So let me give you an example of that. This is an example from a website that way back when I was doing some research came across. I changed it slightly to protect the innocent. And here, this is a problem. If you're dyslexic like I am, it's actually quite a bit of text. Apparently, you need to convert 2.5 gallons of punch into quarts for some type of birthday reason. This visual doesn't do much for me. It's a big thing of punch equals a bottle with an arrow. I don't really know what to make of that. There's a conversion table over here, but it's multiple choice. And so let's see. Let's just try one of these things. So let's try A and see what happens. You're wrong. Try again. Okay, so let's click here, try again. All right, let's try B now. Okay. Ding, 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 you got it right. Did I learn anything? Maybe I learned to guess, but I didn't even read what was on the, I mean, that's one of the powers of being dyslexic. You could decide not to read stuff. It's really cool. But I didn't even look at what was on the buttons. I just clicked. And this is what like 90% of online math learning looks like. You get some choices, you get it wrong, it says, oh, you got it wrong, try again, and you get it right. It's like, yay! Sometimes you get fireworks or some amazing thing happens, and they think that's supposed to be beneficial. And no wonder that almost zero measurable learning happens in that type of environment. So how do you fix this? Well, one way, here's a very straightforward way to fix it. Get rid of the multiple choice and create an open selection, number one. Number two is give feedback. So don't just say you're wrong or you're right. Show the consequences of your solution, and you yourself should be able to tell if the solution worked or didn't work. Okay, so let's try this out. So let's get it wrong first. So let's pick 12 quarts. And now let's watch what happens. So watch up there where I have the 2.5 gallons. Notice I also got rid of a lot of the text. Okay, so there's my 12 quarts, 2 gallons, and here's a half. 2 equal parts, pick 1 part. That's a half. That's what 2.5 looks like. And this is what it means to convert gallons to quarts. So every gallon goes into 4 quarts. So if I didn't know that conversion factor, I could learn it through the feedback. And then half a gallon gives me only half of 4, which is 2. And so that was too many. I had extra quarts left over that I wasn't able to fill with that selection. So it didn't say, you're wrong. It said, OK, if you think it's 12, let's go through the process. And even better yet, in the early stages, let them go through the process. And you can do that digitally. That's only useful for a limited period of time. And then you want to kind of speed up the process. But let's get it right now. OK, so let's pick 10 quarts. OK. So again, the visuals on what the numbers even mean and what the conversion means, and presenting that visually. So 4 and 4.5 of 4 is 2, so 4 and 4 are 2 is 10. And so that's 2.5 gallons converted to quarts. And the penguin was able to get across the screen. And so there wasn't any, if I rotate this thing, it wasn't any fireworks or badges or anything like that. It was like the solution, it worked. And that is actually much more intrinsically motivating than having some extrinsic motivating factors. So this is the straightforward way to address that problem that plagues so many programs.
What age was that?
That you start doing that like in 2nd grade. Yeah. So this conversion problem is probably like a 4th grade, according to but I mean, that type of mathematical thinking starts in 2nd grade is when you start learning fractions and doing conversions and things like that. Okay, so mastery-based schema building. So here is, this is a famous problem. It was mentioned in a paper in the journal Science because it was so remarkable that only a third of middle and high school students were able to answer this question correctly. This is from the NAEP exam. This is the national assessment. And actually it was only a quarter of the students, actually. I think it was only a quarter of the students were able to, yes, only a quarter of the students were able, which is what you would get if you were just guessing. And so, when you ask them, it's not like they didn't have any schema for what was going on. They did have a schema. They look at this stuff and they go, first of all, freak out, because there's big numbers. Maybe they remember to try to find a common denominator, which is hard-ish, unless you just multiply them together. And then if you just multiply them together, but then they're like, wait a second, I'm supposed to be adding. So they add the denominators. And they just basically go and do a bunch of stuff. And they also see a bunch of numbers here. So if they added either the numerator or the denominator, they're going to see one of these two numbers. And they're also big numbers, and they see a bunch of big numbers here. And so they have some really complicated schemas for what's going on that are not very fruitful they're not what's really going on. But this is a very big problem because it's correlated with low performance in algebra, this particular issue of students really not understanding what it means to add fractions. So what do you want them to see here? What you want them to see here is, oh, this is a whole divided into 13 equal parts, and I'm going to pick 12 of those parts. So that's almost a whole. And here is a whole broken up into 8 equal parts, and I pick 7 of them. This is almost this is also almost a whole. So two numbers that are each close to 1 is going to be something close to 2. And you want them to see that instantly, just as I see this and I say that's a chair and this is a shoe. You want them to see this like that's approximately 2 or just under 2. And you want that to be part of your perceptual action schema system. Okay, so how do you do that? Well, we did a study, and this is a very simple game. There's a number line. There's this unique, interesting contraption here, which is a unicycle. And this is a special unicycle because it's going to unravel as it moves. And the goal is, where do I place this balloon platform so that when it unravels and one circumference is going to get you to 1 tick on the number line, where should I put the balloon platform? And so here is a okay, I got it wrong. So here, here is a circumference of 1, so I put it at 1. So where is this one going to go? You don't have to worry about the vertical part right here, just the outer part. So where's that going to go? Right here? You hear whispers like somewhere around, they're saying like a half or something. Okay, a half. That goes to there, okay. And this is a small amount, so it's not going to get you very far. And this looks like it's pretty close to a whole, so it's going to get you almost to a 1. Okay, so once you've mastered that, you're starting to build this perception action schema for what's going on here. Once you've mastered that, you want to move them on. So now let's move them on to, now I have 2 little wedges, 2 little parts of a wheel. And so here are 2 little, two small amounts, so it's not going to get you very far. This is like almost a whole wheel plus like the missing part that would make it completely whole, so let's put it right at 1. And here I have 2 that are each close to 1, so it's going to get you somewhere close to 2. And then once you've mastered that, let's move them on, and now let's introduce symbolic representation. So let's say I have no idea what these symbols mean. And I see a 1 and a 2, and I say, oh, let's make a 1 with a little dash or a little line between them. So I say, oh, maybe that means between 1 and 2. So let's put it here. So that's where I think it means. It would be terrible to say, you're wrong, try again. No, you want to see what this means. Okay, so what does it mean? So let's watch. So 2 equal parts, pick 1. Okay, so that's what that means. And so it might be too fast, so you want to see it again. 2 equal parts, pick 1. Okay, now I'm starting to understand. So this is going to break it up into 8 equal parts. I'm going to pick 1. So that's 1 small part. 8 equal parts, pick 1. And here's 8 equal parts, pick 7. So where is that going to be? Close to 1? Okay, let's try that. Close to 1. 8 equal parts, pick 7 of them. Close to 1. Okay, good. 13 equal parts, pick 6 of them. Is that more or less than a half? A little bit less than a half, someone said? A little bit less? Okay. 13 equal parts, pick 6 of them, a little bit less. Okay, good. So now once you've built up a schema for that, now let's bring on 2 wheels, both in symbolic representation. So here is 8 equal parts, pick 1, that's a small part. 12 equal parts, pick 1, that's even a smaller part. So those are 2 small parts. They're going to get you to a small distance away from 0. And here's that same problem we saw earlier. Whoops, which I got wrong because the thing moved on me. But okay, here we go. 8 equal parts, pick 7, that's almost a whole. 13 equal parts, pick 12, that's even closer to a whole. So 2 numbers that are each close to a whole is going to get you someplace close to 2. And so what we're able to find in 2 weeks, so it takes about 2 weeks, and the literature, especially the rat literature, is very consistent in the mouse literature where they're learning mazes and stuff, very consistent of these schemas to consolidate from the hippocampus into your neocortex takes about 2 weeks to build up a schema from scratch. And so that's what so after 2 weeks of playing this game, you can get virtually all students able to perform additions of fractions approximately. So they're estimating now almost any number any fraction you throw at them. So they've really built a solid schema for what fractions mean and approximately what it means to add them. Now there's a long ways to go to get them to add them precisely and everything like that. But this addresses a serious national issue that we are facing. So this fraction schema, just to really make it clear. So what the schema is that when I see this configuration, just like if I see this thing with a cushion thing and a cushion thing that looks like a move, I know this is a specific type of chair that you find in movie theaters and stuff like that. I look at this and I say, this is a particular type of mechanism where this number breaks something into that many parts, 5 parts, and this number selects that many things. And so we can do this to anything. So here's a circle, break it into 5 parts, select 3 of them. And that's what 3/5 looks like on a circle. We can do it to a starfish. Break it up into 5 equal parts and select 3 of them. We can do it to some gummy bears. Here's some gummy bears. Break them into 5 equal parts. The equal part is important. And select 3 of those equal parts. So this is a generalizable schema for fractions. And this also look on the number line. On the number line, break a whole, 0 to 1, into 5 equal parts, and select 3 of them. And so that's where 3/5 is located on the number line. Okay, so this is a generalizing schema, and you can interact with it, and you can do all the things that you can do with it like you would do with real-world mechanisms. And this is a powerful approach that builds deeper understanding for building up all of those perception action schemas that you have to build in math. Okay. Let's take it one step further, because you're not done with fractions at that point. There's a lot more you have to go. But let's just take it one step further to negative numbers. So -3/4, if I didn't know, one misconception that happens is if they know where 3/4 is, they might think that -3/4 is located here because they're thinking that you're going from left to right. I don't know. So this does happen. We see this happen a lot. Okay, so let's look at that. So 4 equal parts. Select 3 of them. And this is what the negative sign does, is it flips around 0. It's a mirror reflection around 0. Okay, so that's part of the schema, is this mirroring that the negative sign does. So, okay. I don't know why I got it wrong again. Okay, negative flip. Okay, so -3/4 is located there. Okay, so -3/4. 4 equal parts to make a whole, 4/4, and then 3 of them makes 3/4, and then flip around 0 to get -3/4. Okay, so that's a schema that you're building for what the negative sign does, and it's a generalizable schema. So let's now generalize it to double negative. All right, so double negative doesn't mean even more negative. Double negative means I'm going to flip twice. So let's look at that. 4 equal parts equal a whole. 3 of those parts makes 3/4 flip, and then another flip, and I get back to positive 3/4. So why does negative times negative equal a positive and things like that? If you build the right mechanism that's generalized, and then you have this intuition that's solid about how these mathematical principles work. Okay. One really important thing to do when you are building up these schemas is to avoid shortcuts. I don't know how, the reason why almost everybody, including myself, wants to take a shortcut is because these higher association areas in your brain are so slow. The neural networks there are very, very slow to change. And that's a good thing. But it's also, from a teaching perspective, you're like, come on, let's build those neural circuitry here. The hippocampus, fast. And so shortcuts, you can get through with the hippocampus through mnemonics that's stored in your episodic memory instantly, and it feels so rewarding. But it's actually often very bad for mathematical understanding. And let me give you an example, because this is probably the pinnacle of the miserable failures that I have created in my career. So one day, I said, this math facts. We need students to memorize these math facts, and it takes so long for them to iterate over and over again, and I just want them to know it and move on. Maybe there's a faster way to do it. And I said, what if we created little stories? Because your hippocampus can learn stories instantly. Let's create little stories, and they'll learn those stories, and then they'll learn the math facts. And so I tried it. So 8 times 8, let's turn this into a little story, a little visual story. I transform it into, what do those look like? Clouds. Okay, do they still kind of look like 8s? Okay, so let's watch what happens. Some wind blows a sailboat onto the screen. Now, wind does not come out of clouds. Okay, so this is physics. This is terrible. But okay, this is the story. Okay, and do you see? What does it look like down there? 64, right? Okay, so now let's map it back into numbers. Oh, so this is like it's like a terrible story, but it's this little story. The kids loved it, and they could remember it. And so I was like, I'm going to win a Nobel Prize. They don't even have a Nobel Prize for education. They're going to make one just for me. And I was asking this young boy, I was like, all right, what's 8 times 8? He's like, oh, it's the sailboat. It's 4. 4? 4 is less than 8. I'm asking for 8 groups of 8. It's like, yeah, it's 4. That's when I realized that if you create a mathematics program where 4 is a possible solution to 8 times 8, and the student is relatively confident about it, you're doing something really, really bad. And so that's when I realized it's like these mnemonics are just ruining the understanding of what's going on. Because 8 times 8 does not equal 64 because of some story. It equals 64 because of very precise mathematical mechanics. And you want to get those mechanics across. And so it takes longer, but if you do it right, you're building these schemas that are generalizable, that are way more powerful than just memorizing or just knowing a particular fact. So let's look at how to do that. So here's 8, and here's a little 10 frame. So it says build 8. So let me select 8 here. So there's 8. And now it says 8 times 8. So 8 groups of 8. All right, so let's do 8 groups of 8. And now it's giving me a little hint where I can manipulate and move these things around. So I can take this 2 here and move it over to form a 10. And that's the strategy they're learning here. I can move another 2 to form another 10, and another 2 to form another 10. So I'd have now 3 10s and 2 1s on the top. And I can do the same thing on the bottom. So move this over, form a 10, form a 10, form another 10. So now I have 6 10s and 4 1s. And I did that myself. I turned 8 times 8, I built up 8 times 8, and I rearranged them, forming 10s, and I created 6 10s and 4 1s. And in place value, that's 64. So that's 64. So 6 10s, 4 1s. And this is a way more powerful way than a story and a mnemonic. So now this is building the schema. It takes a long time to build up this 10-frame schema, build up this concept of forming 10s and recomposing and decomposing them, but it's generalizable. You can throw now all kinds of problems they've never seen before, and they have now these mechanics, these spatial temporal schemas that they're able to do actions and connect to their perception in order to solve mathematical problems. Okay, that was a very long time on this part of your, of your brain, these higher association areas of your perceptual and action systems. But now I'm going to spend even longer on each of the other subsystems. Does that sound fair? Sounds good. Sounds good, let's do it. Okay, so let's move on to your prefrontal cortex, where you're solving non-routine problems you've never seen before. It's not rote learning kind of like it is back here. Okay, so non-routine problem solving. The best way to do this is just throw a problem out at you guys that you've never seen before, hopefully. Who has seen this type of problem, this game before? Okay, good. So, all right, let's first just try it together. So I have no idea how to play this game. I actually made this game, so but I'm going to pretend like I don't know how to play this game. All right, so I'm going to just click on some things. Rotates like that, rotates like that, rotates like that. Did that look like it solved the problem? What do you think you're supposed to try to do? Match the penguin over there? How did you know that? Did you read the instructions? You're able to just look at the feedback? All right, good. Okay, so do you want to try it? Yeah. Oh, all right, so just tap on those. Tap on, and here it's wanting you to tap on 3 of them, right? So go for it. Oh, you can just tap instead of drag. Just tap on, yeah. So that's going to rotate them like that, or her, like that. All right, what are you going to do next? Okay, okay, so rotating like that, and then you're rotating like this. Okay. Okay, now like that. Okay, rotate like that, rotate like this, and then rotate like that. Now, okay, that's good. Wait, no, you can keep going. You can keep going. Okay, but you now starting to build some schemas for what these rotators do, right? Did they do something slightly different than what you thought they might do?
Yes.
Okay, so, all right. Yeah, the green thing is like a stick, or the gray thing is a stick, which is the axis that it's rotating around. Yes?
When I was seeing that, I was seeing it anatomically, and that the cylinder was to represent the spinal column.
Oh, okay. I see. So it was rotating no matter what the orientation. So that instead of a spatial X, Y, Z, it's relative to the ping. Ah, okay.
How you rotate as a ballerina.
Yeah, okay. Got it.
If you're on a rotisserie or whatever.
You could try anything. Okay, so this one, okay, so this one is going to rotate. Oh, I even have a little penguin right here. So he's now facing in the thing, and so you did like that, so it's going to go, oh, sorry. Yeah, he was now like this, right? Okay. All right, and this one, and you, oh, okay. So then, so now it's going to go this and like that. All right. All right, there you go. All right. You want to solve another one? No. Okay.
One thing that wasn't apparent was that you could use the same thing.
That wasn't apparent, you're right. And so that is one of the tricky so remember, this is a non-routine problem solving where you're supposed to be confronted with unknowns and misconceptions that are imposed by yourself. So one of the most challenging things with real-world difficult problems is you impose more constraints than are actually in the problem. And so you want to have students encounter things like that. Okay, so this is an example. So the basic thing that I wanted to show was you want students to be confronted with problems they've never seen before that are multi-step. That's what your prefrontal cortex is built for, because it has all the working memory apparatus to plan out multiple steps. So you want to multi-step, and preferably you want it to be connected to mathematical reasoning, and if you're teaching mathematics. And so here, does this look like algebra? This is highly connected to algebra. Okay, so I have an input, I have an output, I have some unknowns I'm solving for, some operators. You can think of this maybe a transfer function or something, a function that I'm working, and I have here are some operators that I'm dealing with. I'm solving for some unknowns. It's very algebraic type of reasoning and problem solving. And so you want to approach algebraic reasoning problem solving from all kinds of different angles. And this actually does address a component of algebraic reasoning. So one of the things, so I talked to you about some of the problems, the issues, the fatal flaws with perception action schema building. One fatal flaw is using multiple choice and taking shortcuts. And there's a whole bunch of flaws that are very common, things that people do that are just opposite of what you want to do. For the prefrontal cortex work, one of the big things is the importance of struggle. And no one wants to see their students struggle. And so often, a teacher will come in and rescue someone who is trying to grapple with a really difficult multi-step problem. And struggle is so good. So no pain, no gain, especially for your prefrontal cortex. You need to actually try to grapple with and overcome difficult problems. And so let me show you a quick example, because a lot of people think this goes against Vygotsky. You guys know who Vygotsky is? He's a famous educational psychologist, came up with the concept of zone of proximal development. And very often that concept is thought of as you're making progress, you shouldn't have something that's too difficult, and you shouldn't have something that's too easy. You should have something that's right in your zone of proximal development. And that's not really what Vygotsky said. You want things that are good learning in situations for where you are right then. But in this case, good learning situation means challenging. It doesn't mean just right for you, easy. It means it should be challenging where you can learn and get there. And so periodically, you want things that are seemingly too difficult for where you are right now, but they're within your zone of learning, and through getting feedback, like trying something and see that it didn't work, and they're like, oh, maybe I can try something else. That's good, because you're in an optimal learning situation zone. So you want things that are too difficult, but when students get here, they're frustrated, and they want to give up, and they do give up. But it's school, so they have to come back the next day. But eventually, they figure it out on their own, without the teacher giving them the answer, and without any hints and things like that. They figure it out, and this is what that looks like. This is one of the best feelings that you can have in learning. Does this look like someone who's having fun? This is not fun. I mean, this is related to fun, but this is someone who just conquered something. It's different from fun. It's like this exhilarating feeling that you overcame something that was difficult. You don't feel like this if it was just right for you. You also don't feel like this if someone gave you the answer. You might feel good, but you don't feel like this. You only feel like this if you did it yourself and it was hard and you thought you might be able to do it, but you didn't. And this builds up this thirst for challenge, this intrinsic motivation, and this wanting to be a lifelong learner. And we need a lot more of this. And school does not provide enough challenge and enough support structure. So the teacher is actually doing a really good job where this looks like it's extrinsic motivation, but it's actually supportive of intrinsic motivation. And I won't get into that right now, but so this is really important for building up your prefrontal cortex subsystem. Okay, so let's move down to your medial temporal lobe, your hippocampus. I'm going to refer to it as your hippocampus, which is your episodic experiential knowledge. So when you are designing an educational learning system, most of your work is going to be around building up all these schemas. So be very deliberate about what are the schemas and what are the action and perception components of those schemas. Often, like what I'm doing right now is I'm mostly talking, so I'm doing everything through perception, except for a couple. I had you guys do like a few of you do a little bit of action. You want to think about what are the actions. You also want to see like how much non-routine problem solving and how much challenge to get them. Tax working memory, but not tax it too much, all this stuff. For your episodic knowledge, you want to think, what are the key experiences that I want the student to have? And in mathematics, there's a lot of key experiences, like experience of that flipping. There's a whole bunch of key experiences, but there you want it to be solid as a schema. But there's an experience where you only really need to experience it once. And the great thing about the hippocampus is one time is all you need. And you can remember it forever. I can remember when I was a little kid and my dad took me to the park and I will never forget the smell of the grass. And the hippocampus is so awesome like that. And so you want to utilize it, but you want to utilize it in the right way. So let me show you an example of a mathematical experience. Here I have, I'm on this fraction theme right now. So I have this hole here. This is just to see what happens. Let's just try stuff. So I have these scissors. And I'm going to go cut up a bunch of stuff and watch what happens. Okay, did that look like it solved the problem? What do you think you're supposed to try to do? Divide it into 3 equal parts? Do you think they have to be exactly equal parts?
Somewhat.
They do. Okay. Do you want to try? Okay. What's your name?
Hi.
Okay, hi. Okay, so cut up into 3 equal parts. The last scissor you can use to cut the string. All right, here you go. Whoa. You're very, okay. Oh, okay. Wow, how did you do this? Is that like, it didn't even look like you were trying. All right. Okay, all right. So what, are you an engineer or?
I'm in finance.
You're in finance, all right. Or do you know how to do like archery, or are you really? You play games?
So,
Okay. All right, well, that was pretty impressive because you cut it perfectly into 3 equal parts. Okay. Well, I was hoping you would struggle with that and try. Okay, so let's pretend that you tried several times. And you were really close, but it wasn't exact. And you're like, and let's just imagine that he just did that. Okay, that makes sense that he would maybe not you, maybe someone else. I should have done it. Okay, but so you might think to yourself, why would you want students to go through this tedious task of having to cut things into exactly 3 equal parts? Why would you want that?
Because you want to have the experience of thinking about it and then actually making the decision of where it is.
I like that you use the word experience. Okay, yes. So the definition of fractions, the denominator breaks things up into equal parts. By equal, it means exactly, precisely equal parts. And it's hard to understand precisely equal parts until you've had to actually cut something up into exactly equal parts. And if you don't have that in your experience, you don't really have a full understanding of precision. And so there's another Common Core standard, which is attention to precision, which is another thing. It's an experiential thing, I think. I'm proposing that it's mostly experiential, that you've experienced, but you don't have to get super good at cutting things into exactly 3 equal parts. But you want to have struggled with it. You want to have struggled with it at least once, so you have that appreciation. And if you ever end up given rulers, now you're like, oh, rulers are so great, because now I can get precision and not have to do the estimation. Okay. All right, one other, we're running out of time. So this is a physics example since you teach physics. I'll just give you this example really fast. Here is a van with our penguin driving it, and if the van comes to an abrupt stop, should the balloons go forward or should they go backward? They'll go backwards. They'll go forward, then backward? They'll go back. But then why does the penguin go forward if you come to a abrupt stop? A lot, as you probably know, a lot of even college kids will think that it should go forward because if they have an experience where like their Amazon boxes go forward, everything moves forward when they come to an abrupt stop, and so they think that the balloons are going to do that too, and they haven't probably had experience where they're driving around in a van in a penguin suit with helium balloons tethered to the bottom. That's not an experience that a lot of people have, and so they do have an experience though with balloons. And do they really understand why balloons even go up in the first place? Because going up is not what balloons do. They don't go up. They go where there's less pressure because all the air molecules, they're hitting it more times here and fewer times here, and so you have the balloons are going to get pushed up. And so they're kind of, you can think of it as seeking out lower pressure. Lower density air. Okay, so I'm probably saying all kinds of physically terrible things right now, talking with a physics professor next to me. And so when you come to an abrupt stop, you can think of it as all these air molecules getting pushed up to the front and creating high density here and lower density back here. And so the balloons are doing the normal thing that they always do is getting over to the lower density air. Okay. Tell me all my things I did wrong afterwards. Okay, so that's an experience. This experience and that experience can generalize to understand kind of what's happening. And so this is a physics example of an experience. There's lots and lots of experiences that you want them to have, especially around things that are counterintuitive. Okay, so so you want to plan this out, and this should be fun and should be enlightening and connected. You want to connect these experiences to deeper understanding. And so that's your medial temporal lobe. And then the last area, academic discourse. So academic discourse, the reason I didn't call it the language subsystem is because it's not just about talking and listening. It's about putting your ideas into your own words and hearing other students put their ideas into their own words, and you potentially poking holes in their ideas and having a dialogue and discourse. And so academic discourse, I think, better characterizes what we want this subsystem to do. And let me just give you, I'm going to jump across this example and go to this example. Okay, so here I have some flying fish. And so one way to have academic discourse, I should have shown you the previous example to compare and contrast these two methods, but one way to have good academic discourse is to ask students to use mathematics to describe something that at first doesn't look like it has anything to do with mathematics. That tends to evoke a lot of really good discussions that are really good for building up academic discourse. Okay, so here the question is, do flying fish actually fly? That is a mathematical question. Why is that a mathematical question? So here you'd want to break up into little groups and discuss it. We don't have time to do that. But does anyone have anything about why is that a mathematical question? Do flying fish actually fly? It's a philosophical question, okay.
Everything in the world.
Everything's mathematics. Okay, that's an easy way out. Okay. Okay, so you want to connect it to schemas that you have and things like that. Okay, so here's one way. If a fish was just jumping out of the water, wasn't flying, then I would be able to fit it with a parabola, because things that are just moving through the moving under constant gravity is going to follow a parabolic curve. Okay, so let's close. Okay, so if I was to video record the fish and I could fit it with a parabola, I wouldn't have any evidence of flying. Not that to say it's not flying, because you can fly in a parabola, but that is what you would expect to happen if it was just jumping out of water. But if you video record flying fish, though, it starts off as kind of maybe being able to get fit by a parabola, but it's doing something more than just parabolic motion. And so here I have evidence that there's something additional happening than just jumping out of the water. And this is the start of using, so here I'm using a mathematical concept, a parabola, to start modeling a real-world situation. So this is only the beginning of the discussion, and it's really illuminating to see someone facilitate a really good mathematical discussion. And so the key things that you want them to do is get kids to just try to justify their thinking and try to explain something using mathematics. And once you get that going, you're on your way. So those are the 4 neural subsystems, and we're running up at the end. So I just want to conclude by saying that if we take advantage of these four neural subsystems and create learning environments that doesn't just do one of them, but are doing all 4 of them, but in a very deliberate, well-designed way. So picking out your experiences that are really good experiences, that are kind of myth-busting experiences. You do lots and lots of practice on things that are solid, generalizable schemas. And don't forget about the action part. Connect the action to the perception there. Non-routine problems, you should have multi-step problems. They should be challenging. You should be confronted with problems that have things in there that kind of operate different from the way you've maybe thought they might operate when you first saw it, those types of situations. And then academic discourse. Get kids to put their thinking into their own words and hear the arguments of others and have a dialogue about it, especially something that's kind of fun to talk about. Things that are philosophical are often some things that are very fun to talk about, where you get lots of ideas, and that creates good academic discourse. So if you can create an environment like that, this is not just applicable to math, but any subject area, this 4 neural subsystem approach can be highly effective. And so that's the message I wanted to bring to you today. Thank you. And we have a reception with like...
Oh,
two,
is
right?
there any
Oh.
questions? If you could.
Okay, we have some questions, yeah.
I love your presentations. Just wondering how much time it takes for you to build all the graphics in the games. And that's...
So you have an appreciation for that.
Yes.
Have you coded games before?
Well, I've watched my son try to do it, and there's some software that can help with that whole process. But I'm sure it probably takes still a lot of time to do all of that still.
Yeah, but it's a labor of love, and it's a lot of fun.
I mean, I guess the question is for me is if I want to do something like that, is there tools that help us to try to do the same thing?
You want to do at large scale or a small scale with a small group of students?
Smaller groups.
Small group? Okay, then you don't need any software at all. You can do all this without any software. The trick is to create problems and give them feedback. And so you will then need to give them feedback. That's the hard part about coding games, is the feedback of when you get it wrong, it should show why it was wrong. And when you get it right, it should show why it was right. It turns out that's the hardest part of these games, is to build up really good consequences of your solution. It's really easy to just say, you're wrong or you're right, but it's a lot harder to show what were the consequences of your solution and show them why they were wrong or right. And that's what you really need to do. And so that's where all the coding happens. But you, as a tutor with a small group, you can give your own feedback about that without having to do any coding at all.
Thanks.
What did you use to make the presentation? Oh, sorry. The question is, what did you use to make the presentation?
This is just software I wrote. I mean,
Okay.
yeah. Yeah.
It was good.
Okay, yeah.
I have a couple questions. First of all, do you have some data for this for neural subsystem approach? Certainly you have data using ST Math. Is there data beyond ST Math?
We have an R&D group that has a very data-driven approach, but it's not the same large-scale study type of approach like for ST Math. So in that sense, I wouldn't say this is validated at scale. But what I can say is when you go out and so we've done so many classroom R&D, small little pilots, that the results are off the charts from 2 decades of ST Math experience. Meaning, some of the things that we're doing to get academic discourse, it's really hard to ever get students to say what's in their head. If you're a teacher, you know what I'm talking about. Just getting anything out. That's why wait time. There's all these techniques, and they're very hard to implement. What we found is a way to get students to talk that is very, very effective. And so we don't have hard data for that yet, but it's pretty clear that it's a good approach.
Okay,
If I'm allowed to say that.
And then my other question, so both of my daughters have used ST Math for years. Their principal, who's sitting next to me, has been brilliant in implementing it in their school. And I would love to have it accessible for my high school daughter now.
Yeah.
What is your rollout time for that?
It's probably 3 years.
3 years?
yeah.
Okay, she'll be in college.
One of the breakthroughs that we made on some of these neural subsystems is the need for a narrative component. And so we've been testing out narrative. Narrative's very easy to do wrong, do really poorly. And it's usually done, if you look at the literature, narrative is a bad thing to have happen. But we've found a way where the narrative, the characters embody mathematical concepts, and the backbone of the story is a mathematical story. And when you do that, you get this extra power. So I'm extremely excited about the teenage learner approach that we're currently doing. But it's we're testing in schools this summer, actually, right now, but it probably will be another 3 years before we have a full middle school program. It takes time. Yes.
Oh, that's all right. Good.
So one of my concerns is, and I would say one of the classical tests one could give one to determine whether or not
people are learning basic concepts of math by the time they hit college, or they should have this basic concept even by middle school, I feel. And
Yeah.
one of my concerns is with all the mechanization, I absolutely love the conceptualization you're putting forward. And one of the things that I noticed in one of the slides was a child with a pencil in their hand as well. I think it's probably important to accompany that with physical
Absolutely.
on a piece of paper.
Yes.
One of the classic things I think about when I would show my students is, and I'm teaching math to non-science, non-math students. The classic thing is you go out for lunch with 6 people or 7 people. You each order different things. You decide you're not going to split the bill 7 ways or even 4 ways because, you know, someone ordered something big time and others a couple little time snacks, so it wouldn't be fair.
Okay.
So you want to have something where without getting out their phones, without getting out their calculators, they're able to quickly, by guesstimations like we used to do in old times before computers came around, some of us are older than others, is to guesstimate or also be able to add quickly 4 or 5 different things together to get your entree, your salad, whatever, and know what your bill should be with a group, because maybe you're real stingy and you want to make sure you're not doing any rounding errors that aren't in your favor kind of thing. But things like that, and it's very
Are
concerning.
you going with us to dinner tonight? I just wondering.
No.
Okay, all right. Just wanted to make sure there's, okay.
It's concerning to me that with all the phones and everything,
I
there's
agree
this
with you.
addiction to this thing in the hand.
Yep.
And it's not going thoroughly through the brain to be able to do that in your mind without having to get the calculator out.
Yep.
Because I say, you know, the other thing is a judgment call when you get to your answer. Is that reasonable? And oftentimes there may be a blank stare, which is concerning.
Yes.
And the other thing in that bill would be, okay, figure out your tip. Okay, what's 15%? And that should be an easy thing. You find 10% and add half of that.
Yeah.
So things like that, I'm wondering with all the mechanization and people having an iPad since they're in their crib
Yeah.
till maturity,
Yep.
is that also going to be put in this as a comprehensive package?
Well, okay, so one thing I wanted to point out.
And I love
yeah.
your thing with the block and the 64.
Okay.
That made
Did you see the one with the cycle that falls on the number line and you're adding 12, 13? Okay, so that was an example.
I like the going over with how you negate something and you flip it back and forth.
Well, I think those were examples of like Richard Feynman said, you should know the answer before you go to try to find the answer. You should already know. You should basically you should have an idea of what the answer is before you. Yeah, you should ballpark it. And so I think if you build up those are these approximation schemas of that you should be able to reason about. But then you should also have the mechanisms for finding the precise answer. And what you said about doing it by pencil, it is absolutely critical, and we call that physical ideation, being able to ideate with things that are outside of your brain, like paper and pencil. So I agree with all your comments, basically.
Some things like carpentry or cooking
Yeah.
pull on all that. It's very
Absolutely.
difficult.
Yeah, I agree with you. Yes. Okay.
So at the school where I work, the student, and I think this is typically how ST math is used, but students do math on paper, pencil, that sort of thing. But the beauty of ST math is that they have their own account that they log into. They work at their own pace over the course of the year. And then there's a challenge curriculum at the end of the curriculum, which is really motivating for kids. And so they have the capacity to work at their own pace, work individually as a supplement to the curriculum that's being delivered. So it kind of it's very motivating for kids in that regard, because this is something that they control and work towards that's beyond the curriculum. It supports the curriculum, but it's not independent of the curriculum. Does that make sense? And I think most schools use it.
100% of 75% of the curriculum rather than losing 50% and getting to that, you know, that whole big box of stuff
Depth
you're
over breadth.
supposed to learn, but kind of really not picking up on it, so you
Yeah.
could repeat it 6 months later.
You're saying go deep instead of go broad.
Yeah.
Yeah, I agree with that. Okay.
Hi, I'm what's called a fieldwork instructor, and probably over my 15 years, honestly, I have seen over 4,000 teachers teach. I have seen a lot.
Yeah.
And I collect math stories, and there's a horrible amount of math stories out there. So my concern is that this is not nearly ingrained enough in our curriculums. And I'm also concerned that those teachers who are teaching math, they're petrified when those kids go to take exams, because that's not what those kids are going to see. And so when are you going to reform the testing system?
I'm going to start that tomorrow.
I mean, really, it's what's out there. I know it. No,
Okay.
I'm finished. That's my soapbox.
Okay.
Hi, I'm sorry, I missed the beginning, so I apologize. I don't know
I can
if you.
start over right now if you
No, that's okay. I was curious, you gave an estimation of about 2-week time frame for building the schema for the test that you were showing, the fraction.
Yes.
Do you have disaggregated data regarding specific subpopulations of students with disabilities, students who are
Yeah.
English learners, for particular schema tasks?
No. We have billions of data points we have like right now 1.2 million students using this program right now, and we've been around for 20 years, and so we do have a huge amount of data, but to answer what you just asked is extremely challenging for, first of all, getting the, breaking it down into subgroups. That type of data is difficult to get from schools because of data privacy and all kinds of other issues like that. And then also, anyway, so I'm basically like one of those tennis players that are saying that their elbow hurts before they start playing the game. I'm not able to answer that question. So you're saying, are different types of learners able to learn different schemas faster than others?
Right.
And things like that?
In order to provide kind of an estimation of, one, its ability to support specific populations and showing positive outcomes.
Oh,
and
that we
two-
have.
And two, by population. And then also knowing just how to differentiate for particular learners, how long it may take them to learn a particular,
Yeah.
task.
Holistic on populations for subpopulations like English language learners and all kinds of different subgroups on state standardized tests. We have that data. But as far as how long it takes to learn a particular schema for those different subgroups, that we haven't, that's a whole nother level of sophistication that we haven't gotten to yet.
That would be really interesting.
And 2 weeks, yeah, it would be super interesting. But this 2 weeks is just kind of rough, and that's 2 weeks from basically like building up the whole entire schema, if you will. And so you can, so that's not a exact amount of time. You can do it in 2 days. But you often do want a consolidation period. It means you want to actually sleep on it, because that is when your memory consolidation happens. And so it at least takes 1 day just for that reason. But it is amazing, and so often it's just misunderstood of how much work it actually takes to build up this circuitry. And it's just mind-blowing sometimes. Yeah. Okay. One more question? Is this one more? Last question. Okay.
One second.
Okay.
So one of the things that we talk about a lot is what's the kind of a sweet spot for the amount of time a student should be in the game to have the brain activated enough. So, because we talk about this a lot, like 30 minutes, and sometimes when they're working on it at home, they might work for a couple hours. But what's like the minimum time they should be in the game in order for these brain activities to function at their best?
Okay, so we have our, I don't need to talk, I have my own. So we have our recommended amount of time, which you already know. So you already use our program, which is, 2 45 minutes a week. So one of the really cool things about like just taking the schema development is that you can learn multiple perception action schemas in parallel. So you just imagine a baby learning to walk and learning to eat, and it's not like you first learn this and then learn this. You're learning everything at the same time, and your brain is built to do that. In fact, it's even better. A lot of research shows that actually this cross-training and having multiple things you're learning is actually beneficial. And in ST Math, we don't do that. We teach this subject and then learn this concept first and then move on and learn this other concept. And we do that because we're trying to align with curricula that breaks it up like that. But if we were to blow up education system, we would be building up these schemas in parallel. But it would just blow teachers' mind if we're like learning fractions and learning all these different things at the same time. And it's also very confusing even though it's beneficial, as a learner, you feel like you're a little bit lost. And so it doesn't feel like yeah. And so that's the reason why we don't do that. And the reason I'm saying that is that the answer to that question, I think, is misleading because of all this parallel. So if you're looking at what's optimal, you have to take that parallel processing, parallel learning into account. And so I don't really have a very good answer for you, if that makes sense. I think that's been my answer mostly time, is I just ramble a little bit and then basically say I don't know the answer. Is that, yeah?
He's got a question.
Oh, okay.
No, I don't. I just want to thank our speaker again for a great talk.